Okay, in the last couple videos we looked at unique factorization domains, in other words UFDs, and principal ideal domains, in other words PIDs, and we proved some stuff about them. In this video our main goal is to show that every PID is in fact a UFD, and that actually gives us a bunch of examples of UFDs for free. But before we do that we need some preparation, and one of the pieces of preparation has to do with the following definition. So we say a ring satisfies the ascending chain condition, and that's shortened to ACC, if for every set of ideals ij such that I1 is contained in I2, which is contained in I3, which is contained in I4, contained in I5, and so on and so forth, there exists an n in the natural numbers such that that n kind of stabilizes all of the ideals. In other words, I little n equals I big N for all n bigger than or equal to n. So we cannot have an infinite string of ideals here. At some point they'll stabilize and all be the same. And then I should say that a ring that satisfies this condition actually has a name, and it's called a Noetherian ring after Emmy Noether. Okay, great. So the first thing that we want to prove is the following lemma, which says that every PID satisfies the ascending chain condition. In other words, it satisfies the ACC. And we're going to have to recall the following facts either for the proof of this lemma or for the proof of our big theorem, which is coming up. The first of which says that A divides B implies that the principal ideal generated by B is contained in the principal ideal generated by A, and this should actually be if and only if. Next, A and B are associates if and only if they generate the same principal ideal. Recall, being associates means they differ by multiplication by a unit. And then finally, in a PID, being an irreducible is the same thing as being a prime. And then finally, we'll need this last one, which says that P is an irreducible element of a PID if and only if the ideal it generates is maximal. Okay, so let's get going on this first lemma. We want to start assuming that we have a PID. So let's suppose D is a PID, and we have this set of ideals, ij, where j equals 0 to infinity, maybe we'll go 1 to infinity, is a set of ideals. So in general, the union of ideals is not an ideal, but in this case, we do want to look at the union of these ideals, and that will be a union in this special case. So let's go ahead and set capital I equal to the union j equals 1 to infinity of ij. We're going to show this is an ideal. So recall, being an ideal means it is a subring, and it means that it satisfies this absorption property. So let's go ahead and first show that it's a subring. So let's suppose that A and B are inside this I. So in other words, the union of these ideals. We're going to use the subring test, which means we want to show that B minus A and A times B are in I. That's enough via the subring test. So let's maybe put here that we're going to use the subring test. Okay, good. But being inside of I, that means there exists, maybe let's call it L and K, such that A is in IL and B is in IK. Fantastic. But what we know is that we have this chain of ideals that's ascending. So maybe I should have put that up here. So I1 is contained in I2 and so on and so forth. That means IL is contained in IK if K is bigger than L and vice versa. So, in other words, A and B are both contained in I sub max LK. Because again, it's ascending. Let's say that A is in I10 and B is in I35. Well, by this ascending chain, we know that A is also in I35. Okay, good. But we know this guy is an ideal. In particular, for this part of the proof, it's a subring. But that immediately tells us that we can apply the subring test in reverse for that. So that tells us that b minus a and ab are in I max of Lk. But this is a substructure of capital I. So we have the difference of A and B and the product of A and B inside of I, which means that it is a subring. Now let's go ahead and show that it has the other property of being ideal, the absorption property. So let's go ahead and suppose that A is in I and R is an arbitrary element of the ring D, in this case the PID D. But what this tells us is that A is in IK for some K, because it's in the union of all of them. But because IK is an ideal, we know R times A is in IK, but that's a substructure of capital I. So we have the absorption property proved as well. So let's just underline this. This shows that it's a subring. This shows that it has the absorption property of being an ideal. So in other words, we have shown that this is an ideal. So we're done with this part. Now we just need to show that it truncates in this sense over here. Okay, so I'll go ahead and clean up the board and we'll do that. Okay, we just got done showing that this structure I is an ideal. Next thing we want to show is that this being an ideal leads to this chain truncating and all of the ideals being the same after a certain point. Well, since we're in a PID, we know that every ideal is principal. In fact, that means that I is principal. So we know that I is generated by A for some A in the ring D. Again, that's because D is a PID, which means every ideal is generated by one element. But now, if A generates the entire ideal I, then very simply that means A has to be an element from this ideal I. But then let's recall that this ideal I is the union of all of these IJs. But what that tells us is that A is in IN for some N, which is a natural number, right? So if you're in a union of a bunch of sets, then you have to be in one of the sets at least. Great. But if A is in this ideal, then that means the principal ideal generated by A is a substructure of this ideal. Okay, good. So now let's see what we get out of that. So that tells us that the principal ideal generated by A is contained in IN, but that's contained in IN plus 1, but that's contained in IN plus 2, and so on and so forth. But because capital I is the union of all of these guys are contained in capital I. Great. But then, remember, capital I is generated by A, so we can put capital I on this side over here. But look, we've got a big long string of inclusions of sets starting at I and also ending at I. So what that tells us is that all of these in the middle have to be the same. So in other words, we have IN equals IN plus 1 equals IN plus 2 equals so on and so forth. In other words, IN equals I little n for all n bigger than or equal to capital N. But that's exactly the condition that we wanted to prove in order to show that every PID satisfied the ACC. Now we're ready to prove our main result for this video. In other words, that every PID is a UFD. In other words, every principal ideal domain is a unique factorization domain. And there are actually two things to prove in order to do this. We need factorization into irreducibles in the first place, and then we need uniqueness of that factorization. So let's go ahead and write that down. Factorization in the first place, because maybe if you're outside of a unique factorization domain, there's no notion of factorization in the first place. And then the next thing is we need uniqueness of this factorization. Okay, so those are the two things to prove. Obviously, we need to prove them one at a time, probably. So let's go ahead and prove the factorization first. So we're going to start with D, a PID. Okay, so now let's start with an element inside of D, our PID, and we're going to suppose that it could be factorizable in the first place. In other words, that it is a non-zero non-unit. Because if it's the zero element or if it's a unit, then there's no real good notion of factorizing this thing in the first place. So we want to assume that it's a non-zero non-unit. It could be irreducible, which means the only way to factor it would be where one of the parts is a unit. That would be okay. But maybe like less interesting, but we do want to allow that. Now the next thing that we want to do is write the following. So we'll write A equals A1 times B1, where A1 is not a unit. Okay. So if A is not a unit, then we know we can factor it into two parts where at least one of them is not a unit. Because if both of them are a unit, then their product is a unit. So here we have A1 is not a unit. Now the next thing we want to do is write A1 as A2 times B2, where A2 is not a unit. Okay? And then I think you can probably see where we're going here. We're going to continue this process. So A2 equals A3 times B3, where A3 is not a unit. Okay, and then we can continue this. So we'll write AK is equal to AK plus 1 times BK plus 1, where AK plus 1 is not a unit. But notice this gives us this nice divisibility rule. Notice that A1 divides A, A2 divides A1, and in general, AK plus 1 divides AK. So just by the definition of divisibility within a ring, which mimics divisibility inside of the natural numbers. So that's good. But all of these things, so these divisibility rules, tell us that we have containment in terms of the ideals. So if A divides B, then that means the ideal generated by B is contained in the ideal generated by A. So what this means is that the ideal generated by A is contained in the ideal generated by A1 by this underline, but that's contained in the ideal generated by A2, which is contained in the ideal generated by A3, which is contained in the ideal generated by AK, and then we can keep going. So notice we've built this ascending chain of ideals, but we know that D satisfies the ACC, so there exists an N such that the ideal AN is equal to the ideal AN plus 1, which is equal to the ideal AN plus 2, which is equal to the ideal AN plus 3, and so on and so forth. So now let's take this information, lift it to the top, and then we'll continue on. Okay, so let's see where we are. So we started with this element A from our PID D, and then we factored it first into A1 times B1, then we factored that A1 into A2 times B2, and so on and so forth. In general, we factored AK into AK plus 1, BK plus 1. And then AJ were non-units. So that was our supposition that they were non-units, and that was possible because we started with something that was a non-unit in the first place. From that, we formed this ascending chain of ideals. A is contained in the ideal generated by A1, contained in the one generated by A2, and so on and so forth. Then by the ascending chain condition, these ideals stabilize. In other words, after a certain point, they are all the same. So we have the one generated by AN is equal to the one generated by AN plus 1, and the one generated by AN plus 2. And so on and so forth. But now, in general, what this tells us is that the ideal generated by A capital N is equal to the ideal generated by A little n for all little n bigger than or equal to capital N. But in terms of elements, that means that A capital N and A little n are associates for all n bigger than or equal to capital N. But then what that means is the only way to factor A sub capital N is into P and U, where P is some irreducible. U is a unit. Because if we could factor it into two non-units, then we could keep this chain going. But look, it was impossible to keep this chain going. So in other words, AN itself is an irreducible. So notice what that tells us is that our original A can be written as P times X for some irreducible P. In other words, if we take an element from the PID A, we can factor it into an irreducible times something else. And at this point, X is just something else. Great. And then how do we know we can factor it like this? Well, notice the element A is going to be inside of AN, and AN is irreducible. So that's how we know that. Great. So now I'm going to go ahead and move this to the top, and we'll go on to the next step. All right, on the last board, we argued that if we took a non-zero, non-unit element from our PID, we called it A, then we could factor an irreducible element out of it. So in other words, we can write A as P1 times X1, where P1 is irreducible. So now we can repeat this process on X1 and write X1 as P2 times X2, where P2 is irreducible. And then furthermore, we could write X2 as P3 times X3, where P3 is irreducible. Just repeating the process that we outlined on the last few boards on each of these subsequent X's. So we're repeating it on X1, X2, X3, and so on and so forth in order to pull out an irreducible from the factorization. So in other words, we can write xk as pk plus 1 times xk plus 1, where pk plus 1 is irreducible. Great. But now what we want to do is form an ascending chain of ideals out of these x's. So notice we have x1 is contained in the ideal generated by x2, x3, x4, and so on and so forth. But since this is a PID, it satisfies the ascending chain condition. So that means at some point, let's say xn, although we're reusing n from the last step, it's going to stabilize. So xn equals xn plus 1, and so on and so forth. But what that tells us, again, by the argument that we made in the first place, that xn is an irreducible. But let's see what we have. We have this x1 equals p1 times x2. x2 is p3 times x3 all the way down until we're going to get something like this at the very last step. xn minus 1 equals pn times xn, where both of these are irreducibles. But at that point, we're in a good spot because since all of the p's were irreducibles and we have xn is an irreducible, we have a product of all irreducibles. Let's go ahead and rename xn equal to pn plus 1. And that is going to allow us to write A equals, well, let's just write the first couple of steps. So we have P1 times x1, but now we can write that x1 using this up here. So we have p1 times p2 times x2, but now we can write this x2 using this. We have p1, p2, p3, x3, and so on and so forth until we get p1 up to pn times pn plus 1. And let's recall that we just renamed xn pn plus 1. So let's look at what we've got. We took an arbitrary element from our PID and we have factored it into a product of irreducible elements. So we've completed the factorization part of this proof. Now we need to go ahead and complete the uniqueness part of this proof. Okay, we just got done proving we have a factorization. Now let's prove that that factorization is unique. So let's go ahead and suppose we've got two factorizations. So in other words, we can write A as P1 times P2 all the way up to PR. We can also write it as Q1 times Q2 all the way up to QS. And what we want to show is that R equals S. So our goals are that R equals S and Pi equals some unit times some Qj for some permutation in SR. I'll let you guys look at the precise definition for that. So now we're going to work towards a contradiction on the size R and S. So by way of contradiction, let's go ahead and suppose that R is not equal to S. And without loss of generality, we can actually assume that R is less than S. And now notice that P1 divides A. Well, in fact, P1 times P2 up to PR is equal to A. So that's kind of the definition of divisibility. But this implies that P1 divides Q1 up to QS. But then inside a PID, being irreducible is the same thing as being prime. And so that's what we're going to use. And so since P1 is prime and it divides this product, it must divide one of the terms of this product. So in other words, P1 divides Qj for some j. Now from here what we want to do is reorder so that P1 divides Q1. Okay, good. But now this tells us that Q1 equals U1 times P1 for some U1 which is a unit. Now, how do we know that that U1 is a unit? Because we have factored Q1, which is an irreducible, into parts. But the only way to factor an irreducible is if one of the terms is a unit. So now what we'll do is we'll take this version of Q1 and insert it up here into this equation. So let's see what we get when we do that. That's going to give us P1 times P2 all the way up to PR equals P1 times U1 Q2 all the way up to QS. So I've reordered the right-hand side a little bit. But now, inside integral domains, we have cancellation rules. So that means we can cancel these P1s and then continue on with the process. So notice that P2 divides this right-hand side, U1 times Q2 all the way up to QS. And then after reordering, we can say that P2 divides Q2, but that means that Q2 equals U2 times P2 for some unit U2. But now back into this remaining equation that's left over, we can replace the Q2 with U2 times P2. So we have P2 times P3 all the way up to PR equals U equals P2 times U1 U2 times Q3 up to QR. Great. But then again, we can cancel the P2s, and then we can continue this until we've canceled all of the P's. And we know that we'll cancel the P's first because we've assumed that R is less than S. So after canceling all the P's, we will have U1 all the way up to UR times QR plus 1 all the way up to QS equals 1. All that'll be left is 1 on this left-hand side of the equation. We've converted Q1 through QR into these units, and then what's left is QR plus 1 all the way to QS. But what this tells us is that QR plus 1 all the way up to QS are units. But that's a contradiction because units cannot be irreducibles. Remember, the definition of being irreducible is you are not a unit. And so what have we contradicted? We have contradicted the fact that R is not equal to S. And furthermore, this reordering that we've done right here and here has set up the fact that all of these are associates of each other, which was in fact the other part of the proof. So built into this proof that R equals S, we've also shown that all of the P's are associates of some of the Q's over there. Okay, so this is a good place to stop.